Can everybody hear me?
Yes.
Yeah? All right. So I'm going to talk about the currents in the straits and then relate that to the potential way something spilled in the straits it would be transported. Just an example to kind of illustrate how dynamic the zone is. I work for NOAA, so we have a lab for the Great Lakes located in Ann Arbor. This is a research lab. I'm part of the research arm of NOAA. Just a quick background on NOAA's mission. We aim to understand and predict changes in climate, weather, oceans, and coasts, and this includes the Great Lakes. It's part to try to understand the science and then communicate that to the public. So we have real-time predictive models, probably mostly familiar with the National Weather Service, which is an arm of NOAA. I work in something closer to the National Ocean Service, which means I focus on the water side of that as opposed to the atmospheric side. We share that information with the public through real-time operational models. So the weather models, any weather information you get actually comes from a NOAA model that's run. I should say 99% of the weather information you get. If you're getting marine forecasts for the Great Lakes, that comes from models that are developed from NOAA, but then it's put out through different channels. Local weather outlets, weatherchannel.com, things like that. In the Great Lakes, specifically what that means, or one aspect of what that means, is we develop models, computer models of the Great Lakes for real-time prediction. So we call these nowcast forecast models. Nowcast means what's going on right now in the water, and forecast, and of course, is over the next few days or hours. We implement these into real-time operations, which means they run 24/7, are fully supported, and we disseminate that to the public. So everything that we create goes out to the public, either through website information or through partners through, again, Weather Channel type outlets. One example of this in the Great Lakes is something we developed called the Great Lakes Coastal Forecasting System. This is a suite of computer models. You can go to the website down here at the bottom. There's, again, many outlets for this information. You can get a real-time, again, nowcast forecast information on currents anywhere in the Great Lakes, I should say most places in the Great Lakes. Temperatures, 3D structure, surface temperatures, through the water column, waves, water level fluctuations. So this is both the actual lake level, when say lake levels were low last year, that kind of static information, as well as weather response. You're familiar with the terms called SAISH, which is kind of a bathtub sloshing that happens in the Great Lakes. Also ice, I should say, ice forecasting is done by these models that we run at NOAA. Again, any marine forecast you're getting for the Great Lakes probably comes from a version of this model. Waves in the Great Lakes, water temperature, this is surface water temperature forecast. This is a currents map. Unfortunately, I just have a static image here, but if you go to our page, you can see a live animation of the currents right now in most regions of the lakes, as well as, of course, in the winter ice concentration and thickness forecast. Recent upgrades to these models, they're upgraded pretty frequently. On my scale, they get pushed into operations every several years, as quick as NOAA can take them up. We focus on the Straits of Mackinac. One, because it was not covered in the first implementation of these models about 20 years ago. And we're just now getting around to upgrading the Great Lakes system. And because it's also a very dynamic zone. So as I will talk a little bit about today, and you probably already know, it's a very complex, fast-moving area. And of course, then surrounds important issues such as spill response, or search and rescue, and navigation. So just a quick outline, I'll talk about the currents themselves and how they work. I'll touch on the NOAA real-time model that we're developing just quickly, and then I'll go through what that means as far as a contaminant spill in the area. So quick background on the Straits, you probably know this. Narrowest point, 6 kilometers wide. See a map here, the UP, Lower Peninsula. It's an old river channel that cuts through the Straits of Mackinac that actually drained Michigan into Huron about 5,000 years ago or so. What we do know, what we knew about 100 years ago, this is I'm standing Lake Huron here, looking west into Lake Michigan. So you have the Lower Peninsula here, the UP, and the Mackinac Bridge going across. You can see the river channel cut through here. 100 years ago, they said the net flow, and this still exists, is from Michigan to Huron. So just like all the lakes eventually drain into the Atlantic Ocean through the St. Lawrence Seaway, Lake Michigan slowly drains into Lake Huron at about the rate about 1,600 cubic meters per second. However, what's been observed for probably centuries, and what we've measured in the 70s, again in 1990, and then again last year, is that this flow oscillates. So the flow isn't just this net static flow from Michigan to Huron. It actually goes back and forth between the lakes. Its discharge is over 50,000 cubic meters per second. To give you an idea of that, that's enough to drain Lake St. Clair in a few hours, or drain the Chesapeake Bay in about 7 days. So there's a lot of flow moving back and forth, even though the net is kind of tiny going towards Huron. This oscillation happens over roughly a 3-day period, and what I mean by that is, for instance, if flow is moving into Huron from Lake Michigan, it will go back towards Michigan a day and a half later, and then back into Huron 3 days later. So that's what I mean by a 3-day period of oscillation. It is kind of typical. It's not guaranteed, but that's the average condition. And currents are extremely fast. Currents up to 1 meter per second have been measured and modeled in this area. That's river speed. So I would say that's the extreme. Typically, we see things closer to about 50 centimeters per second. You can do the conversions to English units in your head if you want to. But I'm just giving you an idea. That's very fast. That's much faster than we see in most reaches of the lakes. In the summertime, when the water warms up, the surface water warms up in the lakes, you get what we call thermal stratification. That means you get a hot, relative term there, hot surface water at the top, I'd say maybe 30 to 60 feet. You have the cold water below. This affects these currents in the straits. So when that happens, you start to get the condition where the surface water, the warm water, you can think of it, is out of phase with the cold water below it. That means it sets up in something we call a bidirectional flow at times, or at the very least they're out of phase, such that the currents on the surface are moving at a different pace than those below the surface. Now, as we've observed, it's very complex in the straits I just went over, and as far as we know, these oscillations occur all year long. We've done one measurement of under ice conditions, that was last winter, and the oscillation stayed on through winter. Now, I'll go into an example of how this works, but if the lakes were totally ice covered, Michigan and Huron, this might shut down, but it's tough to say. Complete ice cover in both lakes, I don't think it's ever happened on record, although it gets very close. So what drives the flow in the straits? There's something called SACE, which I mentioned before, which is bathtub sloshing in the lakes. Those have fundamental periods that we can calculate what that oscillation looks like. A lot of times people confuse them with tides in the Great Lakes because they're so regular. In Lake Michigan, that's every 9 hours. You can see a water level go up and then come back down. Lake Huron at 7 hours. The combined lake, because they're actually one lake. We just call it two for I don't know why. The combined lake is about 20 hours of period of oscillation. None of these equal that 3-day period that I mentioned that we observed and modeled. What this actually is something called Helmholtz resonance. And I only mention this just because you're all familiar with it, actually. This is what happens when you blow over a jug or a bottle. You know when you blow over a jug and it makes a sound? So that's actually what's called Helmholtz resonance. And what happens is you blow over the bottle, air goes down into the bottle until pressure builds up and then air comes out the surface. And this is Helmholtz pumping. And it emits a pitch, right? That pitch, that frequency, is the same type of stuff we see in the Great Lakes. Now I'll explain what I mean by that. Consider a weather system is the air blowing over the bottle. Your bottle is the two lakes. So you have reservoir number 1, Lake Michigan, and another one called Lake Huron. As the weather system moves across, this can be wind or even barometric pressure that pushes on the water, drops the lake level in Lake Michigan, for instance, pushes it through the straits into Lake Huron. Lake Huron water level goes up. Then that relaxes, and Lake Huron goes down, pushes water back to the straits, and Lake Michigan goes up. And that will oscillate. So you have this oscillation, but because it's this Helmholtz resonance, we can calculate when that happens based on the size of the lakes, the size of the straits, static conditions due to the topography of these systems. So we come up with something, this Helmholtz pumping is on a period of 2.8 days. So it's very close to what we observed. Again, I'm using some idealized numbers here. So what we see with Helmholtz stuff is the kind of stuff that's driving the flow of the straits. The critical thing, though, that I'll point out here is this is driven by, if you remember, that storm system, in this case, pushing across Lake Michigan, southern Lake Michigan. That could be equally drawn this pushing across southern Lake Huron or somewhere else in the lakes. And that's an important feature because what that means is this is actually driven by non-local weather. So the flow, the primary flow, this pumping through the straits, happens from weather moving across anywhere on Lake Michigan and Lake Huron. Essentially, if I could be down in Chicago and I picked up the lake and went like this, it would ripple through the straits and into Lake Huron and back. So that's what's happening. It doesn't have to be weather right here at the straits, at the straits driving this kind of flow. In fact, most of the time it's not. However, I say, well, based on that kind of condition, you get this nice oscillating flow profile through the straits, back and forth, 3 days or 2.8 if the idealized case was true. But this is modulated, affected by local weather. So that 3-day pumping is happening because weather systems are moving across the lakes. Like right now, we're in this very cold system that's moved across. Hopefully it'll be out soon. But local weather in the Straits, the actual wind conditions going on in the Straits region modulate this signal. So you get something, instead of a nice clean signal like that, you get something a little bit messier. Still with this primary 3-day oscillation, but not so clean looking, right? A little bit more complex. So one of the things we do in NOAA is try to understand not only what's going on out there, but can we predict this? Can we model this so that we have a forecast model in case there's a search and rescue operation or a spill response or any other number of issues that might require forecast occurrence? This is an issue with Mac versus PC, but bear with me. I'll just touch on this quickly. If you want to talk to me afterwards, we have papers on the validation of the model. But we have validation points in the Straits. Particularly, we have current measurements at 3 different locations. I'm showing 2 of them here. We have validation with water level gauges around Lake Michigan and Lake Huron, which are shown in the bottom left. Temperature profiles and surface temperature information. So a lot of validation information that goes into this. This is a plot. Unfortunately, it's a little bit tilted. You can see the model in red versus the actual observed current from a period from last year. So you see this oscillation going back and forth, and the model lines up, in our mind, very well with the observed conditions. There are periods where it gets a little bit out of phase. There's also periods where the model underpredicts the flow out there. That's just a lot due to the uncertainty we have with over-water meteorology. We don't really know how well the wind is forecasted over the lakes, and that's what this model relies on. Now, I'll show an example of what that means, what the model can do for us. So this is an example of this oscillating flow. This is a computer model, again, that I just mentioned that we have validated for the lakes. And what you'll see here, this is a kind of in fast time, but you'll see this oscillation. So you see some movement towards Lake Huron. You'll see it reverse, come back into Lake Huron. You also see that it's not exactly a uniform scenario. So you have maybe some faster currents, of course, towards the middle of the Straits, slower currents and some recirculating areas along the edges. This is just an example of how dynamic this is. Now this is moving pretty quick. There's a timestamp at the bottom if you guys can see that. But again, something dropped in the water there, a person, a ship, a contaminant, anything is going to be moved pretty quick in and out of that Straits. And the exact moment that's dropped depends, then leads to which way it's going to go, Huron, Michigan, or back and forth. Now again, this is just a current simulation. To visualize what would happen if something's actually in the water. Again, a lot of our things are related to search and rescue operations and other types of events. We've also done drifter buoy releases, so we drop in satellite-tracked drifters into the lake and watch where they go. We then use that as validation for the model. We've done this for several sets of buoys, starting in 2014, done some this year as well. These are tracking surface current, so this would be something in the surface where it would go. And it helps us identify also common impact zones. I'll show the first plot here, 3 drifters that were put in roughly at the same time last June. You can see them, they get sucked into Lake Huron. You'll see a reversal here in the oscillation that I mentioned happens. It comes back, they don't quite make it to the Straits, they reverse again. Every time basically they make a turn, that's that suction in the Straits pulling back and forth. You can see most of them, or 2 out of the 3 go down here to south of Boggle Island. 1 snakes up through through Mackinac Island and St. Ignace. We did another set in September of last year. 2 drifters at first. This time they're dropped when there was a westward flow, so you can see 2 of them go into Lake Michigan. 1 was dropped with an eastward flow. You can see the different path that it takes. This is the general situation we get here in the Straits, where you have most things we dropped in the water, I would say all but 1 have gone down this hill south of Oslo. If they're in Lake Huron and Lake Michigan, they snaked up along the UP coast. Now, how does this affect oil transport? Those are drifter buoys. Earlier I showed currents. What does that mean as far as oil? I should say right now, I'm not an oil person. I'm a currents, hydrodynamics, and oceanographic person. So I will mention some of the stuff that NOAA has done, and I've received some simulations of oil trajectories here, and then I'll hand it off to Enbridge, who know much more about this than I do. We did this for a worst-case scenario, and I will loosely define it as that, because I think that will be mentioned after my talk. What we did was we took typical conditions as oscillating flow conditions for real meteorology from 2008, 2-week period of typical conditions, ran the currents for that, then NOAA's oil spill model for basically a line 5 rupture. I show you an anchor strike here. It was really just a generic rupture. Now, before I show these, I'll mention that actual conditions may vary. So you saw that this stuff is oscillating, so it really depends on when something is released into the water, which way it's going to go. But it also depends on the time of month, or time of year, which month it's in. Is it stratified, the temperature or not? Where it was located along, say, the pipeline. What were the wind and wave conditions at that time, and a number of other factors. So this is just an example of the trajectories to try to illustrate the current oscillations that I was mentioning. You can see for an anchor strike here, just be another 30 seconds. For an anchor strike here along the pipeline, 6 hours after that, sorry, I shouldn't say anchor strike. For a rupture along the pipeline, 6 hours later, this is in a westward flow, so the currents happen to be going from here on into Lake Michigan. This is a plot of basically the surface oil forecast based on the currents that we fed into it. You can see an idea of where the blob is going to be, the plume. And then an uncertainty profile. We do perturbations or sensitivity testing to the currents to get an idea of what range this might extend out to. You can see that on the dash line. So we have 6 hours later, stretches 12 hours later, spills moving away from the straits. 24 hours later, this is when the reversal of current starts to happen. So you start to get this stuff sucked back through. It reminds me of kind of a black hole when things get closer to the black hole, they start to stretch out. Picture that. Starts to stretch through the straits, gets pulled back towards Boblo Island, Round Island, starts to go south towards Sheboygan. You can see again this uncertainty circle is growing. As our uncertainty associated with the currents becomes more and more cumulative, I guess you could say. 48 hours later, now heavily impacting Boblo. You can see the uncertainty circle grows, so you would also expect some oil potentially move through Mackinac Island here, maybe even go up towards the UP. And then 60 hours after the spill, probably getting closer to another reversal in the current oscillation where it could get sucked back through. So you can see the uncertainty profile here where you would expect to look for signatures of something out in the water, as well as an area where we have highest confidence that the spill is going to be located. I'll just conclude by saying that, again, this three-day oscillation is very complex, one of the most dynamic zones in the Great Lakes. In the summer, it even gets harder when there's a thermal stratification. And really what this means is this is a rapid transport zone where something dropped into the water, no matter what it is, moves in and out of there quite fast. And we don't know which way it's going to go until you actually drop it in. I'll take any questions, but I think maybe it'd be helpful to hear Enbridge's details on the oil stuff first.